finding all the beta values. Okay, so in this video we will literally find all the values of beta function for any number, yeah, for generalized number. And yeah, I guess if most of you should have heard about the beta function. Yeah, beta function of s is defined as a sum, an interesting sum, that is sum from n equals to 0 to infinity of minus 1 to the power n by 2n plus 1 to the power s. I guess you have heard of the sum, yes. So if let's say if you wanted to find beta of 1, this will be 1 minus 1 by 3 plus 1 by 5 minus 1 by 7. Yes. I think you might have found this sum earlier as well, because this sum can be easily found from the series of tan inverse x as well, because the tan inverse x series is just x minus x cubed by 3 plus x to the power 5 by 5 minus x to the power 7 by 7. Yeah, so from the series you can find its value. What you can do is just put 1 in place of x, so tan inverse 1 will be our required beta of 1, and we know the tan inverse 1 is pi by 4. So beta of 1 is actually easy to find out. Yeah, beta of 1 is pi by 4. Now we also know that this beta of 2, this 1, like 1 minus 1 by 3 square plus 1 by 5 square, 1 minus 1 by 6 square. Yes, though we will find out its value, but it doesn't come out in terms of the elementary functions. Yeah, so that's why we named its value as z, named after Catalan's constant. We call this Catalan's constant. So we see that beta of 2 is z. Yes, again beta of 3 comes out to be pi cubed by 32. We will find this value later on, pi cubed by 32. Yes, so on. There are values we will try to find out. For odd numbers, it comes out to be like perfect answers in terms of pi. For even like there will be answer in terms of digamma. Yes, so we will see that why that happens. Yeah, okay, so I guess now we are ready to begin. Yeah, so before we begin, first of all, know the definition of beta function. The definition of beta function, I have already defined it in terms of sum. Yes, sum from n equals to 0 to infinity of minus 1 to the power n by 2n plus 1 to the power s. Yes. Now we also have an integral representation corresponding to the sum, the integral representation that gives the same sum. I'll just verify that if you want me to. The integral representation is minus 1 to the power z minus 1 divided by gamma of z, and the integral from 0 to 1 ln to the power z minus 1 of x by 1 plus x squared dx. This is the integral representation for beta function. Just to verify, you can just change this to sum. Yeah, this 1 by 1 plus x squared to its sum representation, and then you will see it. So this will be minus 1 to the power z minus 1 by gamma of z, and the integral from 0 to 1, this will just be ln to the power z minus 1 x, and this is sum from n equals to 0 to infinity. This is minus x squared to the power n dx. Yes, now we can take the sum outside, because all these things are constant for sum. So we have sum from n equals to 0 to infinity, and then start to write all the things. Minus 1 to the power z minus 1 gamma of z, the integral from 0 to 1 ln to the power z minus 1 x. Yes, x to the power 2n minus 1 to the power n to the power n, and then dx. Yes, this is z minus 1. This is x to the power 2n. Okay, after this, I guess you know about this gamma integral. Yes, you should have known that this integral from 0 to 1 ln x to the power p x to the power q dx. This will just be equal to minus 1 to the power p, and then gamma of p plus 1 divided by q plus 1 to the power p plus 1. Yes, okay, now if you know this, now you can find this integral. Sum from n equals to 1 to infinity minus 1 to the power z minus 1 by gamma of z. Yes, now this is minus 1 to the power 1, and this integral will be -1 to the power z minus 1. Use this formula, and then gamma of z by 2n plus 1 to the power g. Yes, now gamma g cancel out, and this to multiply to be a perfect 1. So we have that required sum. Do you see that now? So now we have that required sum, that is sum from n equals to 1 to infinity of -1 to the power n by 2n plus 1 to the power g. So this really proves the statement that this integral is also the representation for the beta function. Yes. Now, so we got one integral representation. This will be helpful later on. So let me just mark them. This integral representation will be helpful later on. Yes. And similarly, the sum representation will also be helpful. The sum representation, this will also be helpful later on, while generalizing the how to find beta values. And now in the same integral, if we substitute y is equals to ln x, we get the following representation. Beta of z will be 1 by gamma of z, an integral from if we have substitute y is equals to minus ln x, in that case integral from 0 to infinity y to the power z minus 1 by e to the power y plus e to the power minus y dy. This is also a representation, but we will not really use this, but still you have to know this. We will use the sum in the integral representation in terms of ln a. Now we will use this to find the beta of even values. Yes, and we will use this to find the beta of odd values. There's reason for doing that. Yes. Now the way this method works to find the generalized beta values only works for odd numbers, not for evens. So that's why we had to go to sum for the other one. And the way we do sum, this works for odd numbers as well, but this one gives us more appropriate answers than this. This one just gives in terms of diagonal function. So yeah, this will be for even, this will be for odd either. Now let's try to find the even beta values in terms of digamma. So we know that okay, beta of s is equals to sum from n equals to 0 to infinity of -1 to the power n by 2n plus 1 to the power s. Yes. Now let's say the s is 2a. For s is equals to 2a, but even s, I can say that beta of 2a is equals to sum from n equals to 0 to infinity -1 to the power n. If s is 2a, then we have 2n plus 1 to the power 2a. Okay, good. Now let me tell you one summation idea. Let's say if we are, okay, let me do it this. Let's say if we are summing up from n equals to, let me do another ink. Okay, let's say if we are summing from n equals to 0 to infinity. This is not good. Okay, so n equals to infinity, n equals 0 to infinity of -1 to the power n times an. This will be equals to 2 times sum from n equals to 0 to infinity of a to n minus sum from n equals to 0 to infinity of an. From this, what happens is even terms will be written just two times from here, and over here the even terms will be subtracted once, so there will just be single even terms, and odd terms will be subtracted, but since there are no odd terms over here, so what happens is there are single even terms and single odd terms with negative sign. So I guess you can see how this works. Yeah, we'll use this over here to simplify. Okay, so if we use that for simplification, we get beta of 2a as sum from n equals to 0 to infinity, and then 2 times this thing -1 to the power 2n by 2 times 2n is 4n plus 1 to the power 2a minus sum from n equals to 0 to infinity an is minus 1 to the power n. Wait, now we don't need the negative signs, yes, and we don't need the negative sign over here as well. Why I'm doing that? This wasn't needed. This was not needed. This was not needed because this itself is so that we can remove this term minus 1 to the power n. So I don't really need to write that. That bit. That's I was lost for some time, so that's why I did that. Okay, good. Now 2n plus 1 to the power 2a. Okay, fine. Now after this, I will do something that I will just take 4 out of here, 2 out of here common. Okay, and if I do that, we have 2 by 4 to the power 2a sum from n equals to 0 to infinity 1 by n plus 1 by 4 to the power 2a minus sum, okay, over here 1 by, let me write it again, I will take 2 common, so minus 1 by 2 to the power 2a sum from n equals to 0 to infinity 1 by n plus 1 by 2 to the power 2a. Okay, good. Now if you know this, now this sort of sums can be taken in terms of digamma function. So let me now slightly introduce digamma function. Now digamma functions are defined as digamma of z plus n is defined as negative Euler-Masoni constant plus sum from n equals to 1 to infinity of 1 by n minus 1 by n plus z. Yes. Now if you take its derivative, digamma dash of z plus 1, that will just be sum from n equals to 1 to infinity of 1 by n plus z square. Yes, this is with respect to z. Again, if you take derivative again, yeah, okay, now what I can do with this is digamma dash of z plus 1 is, if I start the sum from 0, sum from n equals to 0 to infinity, I'm gonna get plus 1 over here. Yes, here will be n plus 1, so that is n plus z plus 1 square. I can write it like this. Now I can write z plus 1 as z, so that's why digamma dash of z will be just sum from n equals to 0 to infinity of 1 by n plus z square. Good. Now again, if I differentiate it again, digamma of second differentiation will be, we will have minus 2 sum from n equals to 0 to infinity by 1 by n plus z to the power 3. Yes, differentiate again. Now third derivative of digamma function by minus 2 times minus 3, so we have 2 minus 1s and then 3 factorial will be equal to sum from n equals to 0 to infinity by 1 by n plus z to the power 4. Good. If I differentiate this again, fourth derivative of z will be, again 1 minus 1 will come, so minus 1 to the power 3 will be there. Yes, and then 4 factorial will be there. Yes, let me check if it's going correct or not. Factorial will be there, and then wait a second, and now there will be sum from n equals to 0 to infinity of 1 by n plus z to the power 5. Okay, going good. Now this my 3 and my 5 are, I mean the both are odd, so I can, in place of 3 let me write 5 so that the number is same, 5. Okay, now if I differentiate this again, what do I get? Fifth derivative of z. Now again minus 1 will come, so minus 1 to the power 6 by 5 factorial will be sum from n equals to 0 to infinity of 1 by n plus z to the power 6. Now you might notice something over here. If it's k, here will be k minus 1, and here will be k. So that means sum from n equals to 0 to infinity by 1 by n plus z to the power k is equals to digamma k by z by, sorry, no, this is k minus 1, and 1 less than the number over here, k minus 1 and minus 1 to the power k, and then k minus 1 factorial. So this is the formula that relates sum in the digamma function. So okay, I guess now we have to use this formula to make the progress. So if it's k over here and z over here, digamma to the power k minus 1 of z, like k minus 1th derivative of digamma with input value as z, I mentioned the k minus 1. Okay, I got that. So over here it will be 2 by 4 to the power 2a, yes, and now this will be minus 1 to the power this number 2a, and digamma to the power 2a minus 1 of 1 by 4 by 2a minus 1 factorial. Yes, now minus 1 by 2 to the power 2a and minus 1 to the power 2a, yes, digamma to the power 2a minus 1 of 1 by 2 by 2a minus 1 factorial. Okay, so we have finally done a lot of works. Yes, and I guess we should be closer to the answer. I guess we are doing correct. And wait, no, okay, this is correct, this is not incorrect, this is correct. But also what I could have done for this sum, this is just the sum of the odd terms of a Riemann zeta. Yes, so this also has an alternative expression. This is actually just the sum of odd terms of Riemann zeta. So this could have been easily found out even if we had done 1 minus 1 by 2 to the power that's given over here times Riemann zeta of 2a. Yes, this could have been easily done like this. I just messed up, but I know this is also correct. But yeah, this could have been easily found out just by subtracting the even terms of Riemann zeta function, which is what is done over here. So that's why I can also write this as, the second term can be also be written as 1 minus 1 by 2 to the power 2a Riemann zeta of 2a. Yes, and over here this is okay, and over here this is just 2 to the power 1 minus 4a, because this is 2 to the power 4a, and minus 1 to the power 2a, digamma to the power 2a minus 1 of 1 by 4 divided by 2a minus 1 factorial, and then minus sign. Yes. Okay, so we have finally got an expression for the beta function when the values, the input values are even numbers. So this is what we will use. So let's try to find some values. Yes, I guess it's a good time to find some values. To the power minus 4a, mentioned to the power 2a. Again, mentioned to the power 2a is just 1 itself, so I can cross this out actually, because this is just normal one. Okay, this is the formula. I mentioned to the power 2a is just normal one, so I can actually erase this out. This won't really matter me. Yes. Okay, so now this is the formula. Now let's use some formula to find all the even values of beta function. Yes, and also the Catalan's constant as well. Let's find out the Catalan's constant beta of 2 first. We know that beta of 2, the Catalan's constant. Okay, now we will get the value in terms of diagram function though. That won't be satisfying, but still fine. Now over here for a is 1, yes, 2 times 1, so 2 to the power minus 3, yes, 1 minus 4, and diagram to the power just first derivative, yes, and by 2 into 1 minus 1 factorial minus, and this is 1 minus 1 by 2, sorry, 1 by 2 square, I guess, because 1 by 2 square, 2 into 1 2 square, so 1 minus 1 by 4 is 3 by 4 times Riemann zeta of 2. Yes, so this is digamma dash of 1 by 4 by 2 cube is 8 minus 3 by 4 Riemann zeta of 2. Okay, this is the Catalan's constant. We have already found its value now. Catalan's constant. Now similarly, let us try to find out beta of 4. For that, this is 2 into 2, so the value of a will be, because we had put 2a over here, so now value of a is 2. Now we get beta of 4. Now if a is 2, 1 minus 7, so 1 by 2 to the power 7, yes, 1 by 2 to the power 7. Good. And then digamma of 2 to the 4 minus 1 3. Third derivative of digamma function evaluated 1 by 4 by 2 to the 4 minus 1 3 factorial minus, now 2 to the 4, so 1 minus 1 by 4 is 1 by 1 minus 2 to the power 4 is 1 by 16, so 15 by 16, and then zeta of 4. Okay, good. Then now this will be third derivative digamma function evaluated 1 by 4 by, this is 768 minus 15 by 16, remains zeta of 4. So we also got beta of 4. Similarly, we can get beta of 6. Beta of 6 will be ninth derivative of digamma function evaluated at 1 by 4 by, this will be wait, I don't know. Okay, this is beta of 10. Sorry. How come I should only go to 9 then? So, my bad. Now beta of 6 is digamma derivative at 5 1 by 4 divided by 24760 minus 63 by 64 times remains zeta of 6. Yes. Similarly, beta of 8 will be digamma dash of 7th derivative at 1 by 4 divided by 165150720 minus 255 by 256 remains zeta of 8. Yes. Similarly, beta of 10, this is the last one I'm going to do. I'm going to tell the answer of. So this will be ninth derivative of digamma function at 1 by 4 divided by 19025362940 minus 1023 by 1024 zeta of 10. Okay, so we found out 5 beta values for even numbers. Yes, and you can go on continuing, just substitute the values of a. For this one, a as 1, a as 2, a as 3, a as 4, a as a as 2, a as 3, a as 4, a as 5. Yeah, similarly go on putting other values and you will get all the even beta values. So for this we use the sum, and we got the formula in terms of digamma function and zeta function, and we use that. Yes. Now for the odd, we will use the integral representation to get a nice formula, and that actually gives us some satisfying answers, not like the one that we had now, that we had just now. Okay, now for the next one, again be ready for the next attempt. Yeah, for the odd. Yeah, don't lose the focus. Now we know that beta of 2a plus 1, this is just minus 1 to the power. Okay, so from the like integral definition of beta function itself, over here from this definition, if we put g as 2a plus 1, over here we will just have 2a, here 2a plus 1, here just 2a. Yes, I guess you see that. So let's do that. Minus 1 to the power 2a by gamma of 2a plus 1, and then integral from 0 to 1 ln of x to the power 2a by 1 plus x square dx. Okay, good to go. Now what we do is, now we'll try to break this integral as from 0 to infinity and 0 to infinity and minus 1 to infinity, and then use y equals 1 by x in the second integral. Yeah, let's do that. Beta of 2a plus 1 will be just minus 1 to the power 2a is just 1, so 1 by 2a factorial, and then we will write this as integral from 0 to infinity of ln x to the power 2a, yes, by 1 plus x square dx minus integral from 1 to infinity of ln x to the power 2a by 1 plus x square dx. Okay, good. Now, okay, 1 to infinity, not x, 1 to infinity. Now, if we take y equals to 1 by x in the second integral, what we will get is, okay, if we use y equals to 1 by x, we'll have beta of 2a plus 1, and then 1 by 2a factorial, and the integral from 0 to infinity ln x to the power 2a by 1 plus x squared dx, minus, this will now be integral from 1 to 0, and this will still be ln x to the power 2a. Over here this will be 1 by x squared, so x squared plus 1, and over here x squared, and then minus 1 by x squared dx. I basically changed x to 1 by x, so that's why these things happened. Now this to cancel out, negative sign again reflects the integral, so we have beta of 2a plus 1 is equals to 1 by 2a factorial, integral from 0 to infinity ln x to the power 2a by 1 plus x squared dx. Yes, and now again this minus sign reflects the integral, so integral from 0 to 1 of ln x to the power 2a by 1 plus x squared dx. Good. Now notice that what you need to notice is this integral over here, 1 by 2a factorial, and integral from 0 to 1 of ln x to the power 2a by 1 plus x squared. This integral over here multiplied by 1 by 2a factorial, this is just beta of 2a again, beta of 2a plus 1 again. Yes, so we can use that. We can say that now beta of 2a plus 1, this will just be 1 by 2a factorial. Yes, and then integral from 0 to 1 ln x to the power 2a by 1 plus x squared dx, again minus, this is just beta of 2a plus 1 again. Yes, now this goes to other side, and we have two betas, so 2 goes to this side for division, so we have beta of 2a plus 1 is equals to 1 by 2 times 2a factorial, integral from 0 to infinity of ln x to the power 2a by 1 plus x squared dx. Okay, so this looks good, this looks good. Now the only thing we need to do is we need to see how we can write this integral in terms of some known ideas. Now there is ln and there is x squared, and we'll see how this integral is can actually be derived from other integrals. Yeah, okay, so let me show you something interesting. Now let me show you that we know that integral from 0 to infinity of y to the power s minus 1 by 1 plus y dy, 1 plus y dy, this is just pi, this is actually gamma of s times gamma of 1 minus s. Yes, I guess you know that. Okay, wait, this is nothing. I guess you know that this is gamma of s times gamma of 1 minus s from the reflection formula. So this is pi by sine pi x. Now this is pi by sine pi s. Now if you differentiate both sides with respect to s, then you get integral from 0 to infinity y to the power s minus y, and then ln of y by 1 plus y dy will be just that partial derivative with respect to s of what do we get, and this is pi times cosec pi s. Yes, we get this. Good. Now again, if we differentiate this again, we get another ln y. Yes, so if we go on doing that, integral from 0 to infinity y to the power s minus 1, if we differentiate it 2a times ln of 2a to the power y by 1 plus y dy, if we differentiate 2a times, here we will have partial derivative with respect to s 2a times, and over here we don't do it like this actually. Yes, partial derivative with respect to s 2a times, and then pi cosec pi s. Now we finally have this result, and you might notice that this is actually somehow similar to the one that we are wanting. Here is also ln of x to the power 2a. Yes, and we just don't have x squared over here, so let me try to make that. Let us say that y is x squared. If we do the substitution, now this goes from 0 to infinity, and x to the power 2s minus 2 ln of 2a of x square by 1 plus x square, and then dx is equals to 2x dx. This will be equal to partial derivative with respect to x 2a times of pi cosec pi s. Okay, good. Now I can take this x ahead. Yes, also this 2 comes out, so that's why now we have this 2 and 2 to the power 2a, so that is 2 to the power 2a plus 1, and then integral from 0 to infinity x to the power 2s minus 1 ln to the power 2a x by 1 plus x square dx. This will be equals to partial derivative with respect of 2th partial derivative of pi cosec pi s. Okay, now I can take this to other side, and in this case if we evaluate both sides, 8s is equals to 1 by 2, 8s is equals to 1 by 2. Now we see that this here actually this x goes to 0, and let's take this to other side for division. So we have integral from 0 to infinity ln of 2ax by 1 plus x square dx. Evaluated 8 s equals to 1 by 2. This is just 1 by, okay, now I no need to write absolute number because we have already evaluated this, so it's not necessary to write down now, but for the second integral it is necessary because we haven't really done that till now. Now 1 by 2 to the power 2a plus 1, and then partial derivative with respect to s of 2th partial derivative of pi cosec pi s. Evaluated at s is equals to 1 by 2. This is actually the required answer. Yes, and now so okay, so over here to this integral, I guess now these two are really same. Yes, okay, now yeah, these two are same. Now I'll substitute the value over there. We'll substitute the value. Yes, okay, if I substitute the value, what we get, let's see, beta of 2a plus 1 will be 1 by 2 times 2a factorial. Now you know that this integral is just over here, so 1 by 2 to the power 2a plus 1 partial derivative with respect to x 2a times of pi cosec pi s. 8s is equals to 1 by 2. Okay, now this is around the final step that we are dealing. Now this is 2 to the power 2a plus 2, which is 4 to the power a plus 1, so I can write it as b of beta of 2 to the power is equals to 4 to the power minus a minus 1 of by divided by 2a factorial. Yes, and then for limit s goes to 1 by 2, when s goes to 1 by 2, we want to find this partial derivative 2th partial derivative with respect to s of pi cosec pi x. Yes, pi cosec pi s, and I can, since pi is just a constant, I can just actually take this out of the differentiation and write it over here. So this is finally our treasure. And this is gonna be super powerful in finding any beta values for any a. Okay, let's try and see if that really works or not. Now we know that beta of 1 is just pi by 4, so let's see if we get that or not. Beta of 1, just substitute a is equals to 0, and then we get beta of 1, and this will be 4 to the power minus 1, 0 factorial is 1, and then pi. Now if we partial zeroth derivative is just the original function, so we will have cosec of pi times s is 1 by 2, and cosec pi by 2 is just 1, so this is pi by 4. It works. Yes, now let's try to find beta of 3 as well. So for beta of 3, first of all we need to find, for beta of 3 we need to put a equals to 1. So let's find its derivative of cosec pi s. For beta of 3, put a is equals to 1, so this is 1 by 4 to the power 2. Yes, because 4 to the power minus 2 is 1 by 4 to the power 2. And then since a is 1, now this is 2 factorial. Yes, and then limit s tends to 1 by 2. This is, now this is second derivative, actually second derivative of cosec pi s. Yes, I know now this is gonna be a tough step because finding second derivative is not really a joke. Yes, and I have already done that just to minimize my work, and yeah, that comes out to be okay. So this comes out to be over here, this is just pi times, so let's do it or not. Okay, let me do it. Let me just do it so just for the sake of the satisfaction. Now we know that cosec pi x will just be minus cosec x cot x. Yes, and then again for pi s it will just be pi. So we get this expression again. Now let's differentiate this. We can take minus pi outside and differentiate it. So we get again minus cosec x cot x, derivative of cosec x is, and then over here we will have pi and plus. Now for cosec pi s leave as it is, and for cot pi s that will be minus cosec square pi s. Yes, and then again pi. Okay, good. Now substitute s as 1 by 2. This is our second derivative. Yes, now substitute s as 1 by 2. So we get minus pi, and this will just be minus 1, and cot pi by 2 is actually 0, so that goes to 0 into pi. Yes, plus. Now cosec pi by 2 is again just 1. Yes, that will just be 1, and over here again cosec square pi s, that will also just be minus 1 now, and then pi. So this actually just gives us minus pi times minus pi, which is pi square. Okay, pi square looks good. Now this is just pi square. Over here we have pi by 32 times over, this is just pi square, so we get pi cube by 32. Yes, and that was the answer I told in the beginning as well. So we have found beta of 3. Now we can similarly by this algorithm we can also find beta of 5. Yes, I have already found out the values, and this comes out to be 5 pi to the power 5 by 1536. Yes, similarly we can find beta of 7, which comes out to be 16 pi to the power 7 divided by 184,320. Similarly beta of 9 comes out to be 277 pi to the power 9 by 8257536. These are some values, and I hope this does satisfy your desire to learn. Yeah, now with these two formulas for beta of even and odd, we can literally find out every beta values. That was what I promised in the beginning of this video, and we have done it. So first of all, we went for the Sawmill integral representation. We changed Sawmill representation in terms of diagonal function, integral representation in terms of the partial derivative of cosec x, and that's how we were able to find it out. I hope you enjoyed this video. If you have any doubts, you can go back and check them again. Yes, you will surely enjoy it. I did for the first time. Yeah, now also I'm enjoying, and hope this does like increase your love for beta function and how you deal with it. Hope you got something. Hope it was helpful. Thanks for watching, and look forward to seeing you in the upcoming videos too.